Okay, let's begin here. Um, Today, I want to continue on with talking about gases. Okay, so it's a box with many molecules inside, and now I want to consider, what happens if there are interactions between the molecules. Okay, so the situation that I'm thinking of, is this box, and there's a lot of different molecules, but there's some kind of interaction now so that the molecules feel each other's presence. They don't just feel gravity or feel the walls of the box. So now there's going to be an interaction between each pair of molecules, right? So interaction between those guys, those guys, those guys, those guys, and so forth, right? And so all of that can go into the potential energy, right? So we could say that there is some potential energy, which is the sum over pairs of molecules. So molecule number I interacts with molecule number J. And let's say that there's an interaction potential, U, which depends on the distance between them. Okay, so the distance between the position Ri and the position Rj. Now, the specific form for this interaction potential will certainly depend on what type of molecules you have. Right? It'll be different for argon versus oxygen or nitrogen or any other kind of molecule. But in general, the interaction between molecules looks something like this graph that I will sketch. Right? So if we look at the interaction U as a function of the distance between the molecules R, it generally has a shape something like this. Okay, so that is to say that when the molecules are extremely close together, there is a repulsion. So there is some minimum separation between the molecules. If you try to push the molecules together, at some point they overlap and they can't go together anymore.
Question, real quick.
Please.
Is this the same trend for the nuclear force? The thing like where the force starts to overlap? Because I feel like I've seen this graph before in Intro to Nuclear Physics. Is this the same thing for the nuclear force?
I'm sure it is something like that. I don't know a lot about nuclear physics, but you're speaking about the interaction between protons and neutrons inside a nucleus?
It's like the Leonard-Jones potential, yeah.
Like the Leonard-Jones. Yes, and basically that's what I'm sketching, right? So Leonard-Jones potential is one mathematical expression for this. And so that is saying that there is a U of R is something times 1 over R to the 12th minus something times 1 over R to the 6th. Okay. And so
yes, Jonathan, I think okay. I, I think in nuclear we also have a similar kind of potential like Morse potential, and Corin talk about Yalze potential. I mean Yalze potential. We also have van der Waals potentials. Expression will be different, but we always found this kind of potentials even in nuclear system.
Yeah, it's a very general thing. Although I'll tell you in my very limited understanding of quarks, right? One thing I know about quarks is that at large distances, the potential just keeps going up. And so you would have a trend that's not flattening out, but it would be just going up like this for quarks. And that's why quarks are strongly bound together, right? That you can't separate quarks. If you try to separate the quarks inside a proton, the potential energy would just keep going up and up, right? And that's not the case for typical molecules that interact. For typical molecules that interact, if you try to separate them, the potential energy goes to a constant, right? And so that means the force dies away because the force is the derivative of the potential energy. So that is this long distance behavior, right? That is at longer distances, there is some attraction between the molecules. So at short distances, the potential energy tends to push the molecules apart in order to get to the lowest possible energy. And at long distances, it tends to pull them together. And then the attraction for molecules, as opposed to quarks, tends to die away at very long distances. And you go to some approximately constant potential energy. Okay. So these are the two main features that we want to put into the theory, the repulsion and the attraction. Okay, and so I'm going to show you how those go into the theory. Okay, so suppose we wanted to just continue the same kind of procedure that we had before of constructing the partition function and doing the integral. Okay, let's see how that would work. So then we would work out a partition function that is the 1 over n factorial h to the 3n, and we would have an integral over all the positions and all the momentum. So d cubed r1, d cubed p1, d cubed r2, d cubed p2, okay, and etc. for all the molecules. Now we need an exponential of minus the energy divided by kT. Okay. Now the energy is the kinetic plus potential. Okay, so there's the kinetic energy. That's just the same as we had before. Okay. And now there's also the potential energy. So sum over I and j of this potential energy in terms of Ri minus Rj. And all that divided by kT. Okay. Now, let's see if we can do the integrals the same way that we did before. Well, we have position integrals and we have momentum integrals, just like before. For the momentum integrals, no problem. We can do those just the way we did before, because we still have the same dependence on momentum inside the integral. Okay? So we can factorize it the same as before. So we get an integral over momentum P1 of e to the minus P1 squared over 2m kt. Right? And that's all that depends on P1. And then we have the same thing for P2. E to the minus P2 squared over 2mkt. And the same for P3 and P4 and so forth. And then we have the position integrals. Right, all the position integrals, and the potential energy depends on position. Okay, now each of these momentum integrals is independent of the other ones. So I could put parentheses around each momentum integral. And you recall these are integrals over all the possible momenta. So the x component goes from minus infinity, the y component goes from minus infinity to infinity, the z component goes from minus infinity to infinity. And so each of those integrals becomes, oh, exactly the thing that we were working with before. What is that? The 2 pi mkt to the 3/2, right? So we get that for the integral over momentum 1, and we get the same thing for the integral over momentum 2, and so forth. No problem. Now, we go to do the position integrals. Here, we have a big problem. Okay. The big problem is that now the integrals don't factorize. That is, I cannot take this thing and say, oh, it's an integral over R1 of something that depends only on R1, and an integral over R2 of something that depends only on R2, and an integral over R3, something that depends only on R3, right? This doesn't work. It doesn't work because R1 goes into some interaction up here that involves R1 minus R2, right? The potential energy of R1 minus R2. Right? And so you can't do the R1 integral independent of the R2 integral. Right? You have to do the R1 and R2 integrals together. Okay. Now, can you just do R1 and R2 together? No, because there's some interaction between R1 and R3, R2 and R3, right? So you have to do R1, R2, and R3 together, right? But those molecules are interacting with R4, right? They're all interacting with each other. So there is no way to factorize this into, whoops, wrong pen. There's no way to factorize this into the product of independent integrals. Okay. So this makes the interacting gas fundamentally more difficult than the non-interacting gas. Right? So this kind of goes to the question that Chris asked when we were talking about the magnetic system of, you know, how much harder is the interacting than the non-interacting, right? It's vastly harder because you can't treat each degree of freedom separately, independently of the others. They're all linked together. So this is a big challenge in statistical mechanics, right? How can you deal with problems like this, where there are many interacting degrees of freedom? Okay. There are various approaches for this, right? So, one kind of approach is just, to use a really big computer. Okay? And so you might say, well, I can't have 10 to the 23rd molecules, but maybe I'll simulate 1,000 molecules or 10,000 molecules. And I could do the integral over thousands of degrees of freedom, including all the couplings. That is one approach. Okay? Here, I'm going to tell you about a different approach, okay? And so a different kind of approximation which can make a solvable problem. Right? And so the approximation that I want to show you is a type of mean field theory. So you remember we talked about mean field theory applied to the magnet back a week or so ago. Now I'll show you something which is, conceptually similar, a similar sort of idea, but mean field theory applied to this interacting gas system. And the version of mean field theory applied to the interacting gas is called van der Waals theory. So the idea here is that we want to make an approximation which is to assume that each molecule fluctuates independently. That is, in other words, we are going to neglect correlations between molecules. And instead of considering all the correlations, we will suppose that each molecule moves in an effective potential from the other molecules. So, one way to visualize this is to, imagine that, you're a person who's walking through a crowded train station, right? So back in the days before social distancing, before the pandemic, right? So if you're in a crowded train station and you keep bumping into people all around you as you try to walk through, okay? And so you don't, stop and have a conversation with each person, right? You just feel that there's kind of a pressure of people all around you. So you experience the average influence of all of the other people without really thinking about your correlations with any of the particular individual people. Okay? So the way that works with molecules would be to say, if I have this box full of molecules, and so we have a lot of them here, and I'll think of one of them, which I'll draw in red, as being the test molecule. Okay. So if I concentrate on the test molecule, I'll say it experiences an average effective potential, which comes from its interactions with all the other molecules shown in black. Okay. And so instead of adding up all the separate interactions of this pair and this pair, this pair, this pair, whatever, right? I'll just say, suppose there's some effective potential. We'll call it U effective of R, which depends on the position of the test molecule. Okay, and so this sort of thing is analogous to gravity. Because you remember when we were talking about gravity in the last class, right? Gravity was just a potential energy that acts on each molecule separately instead of acting on pairs of molecules, right? So here, even though there really is a pairwise interaction, one molecule with each of the others, instead, I will treat it as if it's an average effective potential that's just acting on the test molecule by itself.
Excuse me.
Please.
I think because there is translational symmetry and rotational symmetry in fluid, right? So, so I think the effective potential should be independent of the position R, right?
Okay, so you're leading up to the point that this should be a constant independent of R, right? So all I need to do is figure out what's the constant.
Right.
That's approximately correct, as I will show you in just a moment. Yes.
Okay.
Mm-hmm. Mm-hmm. Okay. So now, and then of course, there's nothing that's really special about the test molecule, right? All the molecules are equivalent to each other. And so whatever we do for this test molecule, in the end, it's going to come down to doing exactly the same thing for all the other molecules as well. Okay, so now let's see if we can make a partition function the same kind of way that we did with gravity, okay, with a single molecule potential. Okay, so this will be our approximate partition function, okay, with this mean field assumption. So what we want to do here is to say that there's this partition function, which is, as usual, 1 over n factorial h to the 3n. And then there's going to be an integral over the position and momentum of the test molecule. So an integral over the momentum of the test molecule and an integral over the position, like that, of the exponential of minus the energy of the test molecule divided by kT. So that's minus p squared over 2m plus u effective of r, right, divided by kt. And so this is what you get integrating over the coordinates for the test molecule in red. But because all the other molecules are really the same, they each give a power of this same integral in the square brackets. All right, and so we'll just raise it to the n power, where n is the number of molecules. Now, if we want to do this, we can, of course, do the momentum integral, right? And so we have the momentum integral with the things that depend on momentum. This is still just the same as always. And then the position integral, e to the minus u effective of r divided by kt, all raised to the n. And this is the thing that I've been talking about all along, the 2 pi mkt to the 3/2. Okay, so now, what is this? Okay, well, of course, I haven't yet told you what is the effective potential, and so we don't know how to do this until I make up some form for the effective potential. Okay. So I want to make up a form which includes the important features that we talked about at the beginning of the class, right? The features of short-range repulsion and long-range attraction. So let's try to describe that, okay? So how can we put both kinds of features into this integral? Well, first of all, let's think about the short-range repulsion. You remember that whenever you have two molecules interacting, there are places where this test molecule cannot go, right? It cannot go where this neighbor is. Right? That is to say that there is some excluded volume. There is, a forbidden volume. There's forbidden zone, like they would say in a science fiction movie, right? And so, the physics word for that is usually excluded volume. Okay? So when you have one molecule moving around, here's my test molecule, it can't go where this molecule is. If there's another molecule up here, it can't go there either. Right? So each separate molecule in the system, each black molecule creates a little forbidden region for the red molecule. Okay? So we can add up all those forbidden regions, okay, and say, what is the total excluded volume? Okay? So let's suppose each neighbor, or I won't say neighbor, I'll just say each other molecule each non-test molecule creates a certain amount of excluded volume. Let's just make up a name for that, a variable name for that. Let's call it B. Okay, so B is some quantity with units of volume. Okay? And, you know, it'll be something like a typical size of a molecule cubed, right? So if the molecule has a size of 1 nanometer, it'll be something like 1 nanometer cubed. Okay, and so that means if we have a system of n molecules, that means there is a total excluded volume, which is B times the number of non-test molecules, which is n minus 1. Now, n, of course, is a huge number, like 10 to the 23rd. So if you have 10 to the 23rd or 10 to the 23rd minus 1, it doesn't matter. Okay, so we'll just say this is approximately equal to B times n. So there is a total region where the test molecule cannot go, which has a volume of B times n. Right? Now, the total volume of the box is V. Okay? So that means we could say, well, where can the test molecule go? Okay, so that's the allowed volume. That is V minus Bn. Okay, it's all the places where we can put the test molecule is the volume V minus Bn. Okay. So that can now go into the integral for the partition function, right? The integral up here. You remember, this is an integral over all the possible places for the test molecule. Okay, so that means it's an integral over this allowed volume, the V minus Bn. We could then, here, let me copy this. Copy. Okay, I guess. All right, so when we're doing this integral, we could say this is an integral over the region of volume that is allowed, which is V minus Bn. Right? Or, you know, another way I could say that, another way to say the same thing that I just said, right, is to say U effective is equal to some constant in the allowed volume, and it's equal to infinity in the excluded volume. That is, it would take an infinite amount of energy to put the test molecule into the excluded volume. So this is approximately what Cheng was saying a few minutes ago, right? That there's a constant effective potential everywhere, except that it's infinity in the places where the molecule can't go at all. So that means that for this integral, when we have our integral over volume of e to the minus u effective of r over kt, based on this argument, right? This is an integral over the allowed region of e to the minus constant over kt plus an integral over the excluded region of e to the minus infinity. But e to the minus infinity is 0, right? And so that just doesn't contribute anything. And so we now have what's left is just this integral over the allowed region of a constant. So it's just the allowed volume times that constant. So it's V minus Bn times the constant. So e to the minus constant divided by kt.
Quick question.
Oh, please.
So how does the excluded region change depending on temperature?
It does not depend on temperature. It depends on the number of other molecules that are in the system.
Okay, but isn't it so that at high temperature you can effectively fuse molecules, therefore allowing more of the excluded regions?
Yes, what you are saying is physically correct. It is not included in this approximation. But there could be certainly systems where the core is not hard, right? I mean, here I'm imagining the molecules as if they are infinitely hard, so they just can't get pushed together, right? But you might have molecules that are softer than that. So if you have a high temperature and you have very strong collisions between them, then they can push into each other a little bit, right? And so what you are describing is a correct physical thing, which is not included in this theory, right? But it could be included in more advanced theories, right? But this theory is just the basic thing for a hard repulsion between molecules.
Thank you.
Right. Okay, so now the question is, I've got this constant right here, this constant. How big is that constant? Okay. Well, that involves the other part of the interaction between the molecules, okay? And that is the, long range, the long range attraction. Right, you remember that we have a potential energy that looks something like this, okay, for U as a function of R, okay? And so, if you eliminate the excluded region, right, if this is the excluded region, then out in the non-excluded region, there is mostly a negative potential energy between the molecules. Right? And so there is going to be some negative potential energy out here. So we could say, if we want to know, we're going to neglect all the correlations between the molecules, and we'll just say the test molecule moving around feels an average negative potential energy that comes from its interactions with all the other ones that it approaches. Okay, so that means that our U effective of R in the allowed region, that the U effective of R is approximately this constant. And so what can we say about the constant, right? Well, for one thing, we think it should be negative. Okay. For another thing, it should be proportional to the density of other molecules, right? Because we get a negative potential energy for each interacting pair of molecules. So if there are a lot of interacting pairs, then there will be a lot of these negative components. Okay?
Excuse me.
Please.
I think the potential, this constant of the effective potential should be proportional to V to the power of 1/3. Because if we put all the molecules in a cubic lattice, then the potential should be proportional to the lattice spacing, right? So, so lattice spacing is equal to, is proportional to V to the power of 1/3. So I think this effective potential should be a constant proportional to the volume to the power of 1/3, right?
I would say it a little bit differently, okay? So suppose we say each molecule interacts with others out to a certain distance, out to a distance, I don't know, D, okay? Or no, I won't call it D, I'll call it Rmax. Okay, a certain maximum radius, right? So for any molecules out to a distance Rmax, you feel an interaction. Out past the distance of Rmax, you don't feel very much, right? Out past the distance Rmax, you're out here, right? So maybe Rmax is something like there. Okay, so that means you're interacting with the other molecules, within a certain volume. Okay, so the interaction volume will be something like 4/3 pi R max cubed. Okay? So then we could say how many molecules are in the interaction volume. Okay? Well, that's about the volume times the density of other molecules. Okay, so the number of molecules in that volume, that is something like 4/3 pi R max cubed times N over V. Okay, because N over V is the density of other molecules. Okay, and now this has the right dimensions, right? It's dimensionless as it should be. It's just a number of molecules. Okay? And so then the effective potential energy is going to be some negative constant times this number of molecules.
Right.
So it will be some negative constant, which is, I don't know, something like this amount, okay? So some negative, I'll call it constant prime, okay, times this number of molecules. So that is 4/3 pi R max cubed N over V.
Mm-hmm.
Now, here we have a whole bunch of constants that I don't really know. So let's take this whole bunch of things that I just circled, and I will just give it a name. I will call it A. So A is a constant with units of energy times volume. And so A will be, some constant that characterizes how much is this effective negative interaction potential, okay? And I'm not going to worry about the details of where it comes from, of this constant prime and the R max and all that stuff, right? I'll just say, I'll take all my knowledge or all my ignorance about the interacting gas and I'll put it into this parameter A. So now let's put that into our partition function. So now we have this thing for the position integral. Okay, so whoops, I meant to lasso that. Let's lasso this. So I will take this. Okay, so this is our position integral, okay? And so this is approximately V minus Bn. And now I'll put in the thing that I just calculated there, or the thing that I just kind of estimated there. That is, it's an exponential of positive A times this volume, A times the number of molecules divided by the volume, and here it's still divided by KT. So that means then that I can go into the partition function for the whole system, and that is approximately 1 over n factorial h to the 3n. And now I have this momentum integral, the 2 pi mkt to the 3/2. And the position integral, which is V minus Bn e to the An over Vkt, all raised to the n power. So this is the van der Waals theory for the partition function. Okay? And you can see that it includes two parameters that we don't actually know, right? I mean, it includes B and A. Okay, so these are two parameters that describe these two features of the gas, the excluded volume and the long-range attraction. Now, I know I had a lot of sort of rough arguments to get to this point, but now that I am here, I can do real mathematics with it, right? And so the arguments to get to this point, this is what we often call hand waving. That is to say, when I can't really derive something, I just say, oh, well, the molecules are like this, right? I wave my hands around in different ways, okay? Okay, now I'm finished with hand waving for the moment, okay? And I actually have an algebraic expression that we can work with, okay? I'm just gonna do a couple of quick things here and then I'm gonna stop for today, okay? So to do a couple quick things, right? One thing I can do is get out the free energy from this partition function, right? So there's a free energy, wrong pen, a free energy, which is minus kT log z. Okay. So I can work all this out, again, using Stirling's formula to approximate the factorial. Okay. And I will, let's see, I will mostly just copy this, but let's see what I can do. So this is minus kT n, and so so it's n copies of the log of what's inside here, right? Of the log of this thing, right? So the log of 2 pi mkt to the 3/2 v minus bn e to an over v kt, right? And then all this has to get divided by h cubed inside there, right? And it is divided by n that comes from the approximation for the log of the factorial, right? And it gets a factor of e. I skipped a few steps because I'm running out of time, but we can go over those if you need to. Okay, now the one simplification that I will point out is that we can simplify the log of this exponential because it's a natural log, so it's the opposite of the exponential. Okay, so if I copy that onto the next slide. All right. So we can simplify a little bit more. Minus kT n log of 2 pi m kt to the 3/2 over h cubed and e. Okay. So if I combine this v minus bn and this n, I get v over n minus b. And then I can say minus KTN times the log of this exponential. So that is AN over VKT. And then, of course, the KTs cancel, and there's a AN squared over V. So this is the free energy with van der Waals theory. Okay. You remember when we were doing the ideal gas, we had to, if we care about a system with variable volume, we have to go from the free energy to the Gibbs free energy to include the pressure volume term. That works in just the same way here. So the Gibbs free energy would then be KTN log all this stuff, 2 pi m KT over 3 halves h cubed, V over n minus B, minus, I have this thing, AN squared over V plus PV. So this is the Gibbs free energy for the van der Waals theory. And then the last thing that I'll do for today is to say, what is the optimum volume, right? So if the system is free to change its volume, then it will minimize the Gibbs free energy, which means that we want to set the derivative dg dv equals 0. And that derivative is what? It's minus KTN, and then the derivative here is what? Being divided by V over N minus B times 1 over N, I guess, okay? And then here I have an extra term that depends on V, the A term right here, and the derivative of that is plus a n squared over V squared, and then plus the pressure. Okay, did I get this right? I think so, okay. So this is just an equation that we want to simplify. Okay, let me quickly simplify it. So we have all of this stuff. Okay, if we want to simplify that, that means maybe we will multiply through by, well, first I'll move things around in kind of a conventional way. Okay, I will say P plus AN squared over V squared is equal to KT divided by V over N minus B. Okay? Or in other words, it's equal to NKT divided by V minus BN. So we get P plus AN squared over V squared times V minus BN is equal to NKT. Okay, so this is what I wanted to lead up to for today. Okay, this expression is called the van der Waals equation of state. And this is something which some of you might have seen in chemistry classes or other classes. This is a modification of the ideal gas law, right? The ideal gas law is PV equals NKT. And so here we can see there are two modifications of that. There's this modification, which involves A, and there's this modification, which involves B. Right? So the ideal gas would be if A and B are both 0, but for the van der Waals gas, it's a little bit different. And so we get this equation instead. Okay, I'm over time. I'm going to stop here, and I'll be glad to answer any questions. And then in the next class on Monday, we'll talk about different ways to interpret this, what it all means. Okay, thanks you all. Sorry for going over time.